Okay, so last section we're going to look at for this week is 3.2. And as I said, it's on three different things: continuity, intermediate value theorem, and end behavior. So, most graphing calculators, especially older ones, always assume that what you want to draw should be connected. Right? So if I take my calculator, this is a graph that should be connected. It's a polynomial. Now, if I draw something like this, 1 divided by x minus 2, and I put that bottom in parentheses, what value are you not allowed to use for x? 2. So you're not allowed to have 2 in your graph. That means you're going to have a graph here that's not connected. And older calculators would draw it, I'm going to show you, like this. Remember, calculators, older ones always assumed that it should be connected. So what I basically did is I told my calculator, by turning off this thing called detect asymptotes, that, you know what, just pretend like it's connected and do the best you can, even if it's not supposed to be. Well, if I do that, the calculator gives me kind of a weird looking graph. It's trying to connect it at 2, right? And we said that 2 you couldn't use. It shouldn't be doing that. What it really should look like is this. And this is what newer calculators have. It can detect when a graph should not be connected. And now it draws it a little slower, but it actually draws it properly. Okay? Older ones don't do that. They always draw that weird line in there and connect it. Okay? Newer ones can handle ones that are disconnected. So, actually, it's basically what I just drew. Okay? When I drew that, you saw what happened. The question I'm going to ask you about that one is, could you trace that entire graph right here without ever lifting your pencil? No. You have to. Right. Let's try this one. This is the integer function. Okay. If you remember this one from a couple weeks ago, it looks kind of like a set of steps. Can you trace that graph without lifting your pencil? No. Different reason why, but you still can't do it. Okay? You'd have to lift your pencil up to draw that graph. Now, how about this? That's a parabola. Could you draw a parabola without ever lifting your pencil? Yeah, that one would be fine. Okay? So these first two, you couldn't. This last one, you could. So we're going to talk about what it means for a function to be continuous versus discontinuous. So a function is continuous over a certain interval, which I'm just going to call that interval j. Call it whatever you want. But a function is continuous over an interval if, okay, for all points in that interval, it's basically possible to trace the graph without ever lifting your pencil. That's what it means to be continuous. Now, lifting your pencil, that's not really like a real mathy kind of way to explain it, but it conveys the point very simply. Right? So the idea is the interval j would have a starting point and a stopping point. That's what this a comma b means. A would be where you start, b would be where you stop, and you can trace from a to b without ever lifting your pencil. Right? So if I take this graph and I say a is here, b is here, and I ask you, is that continuous over that interval? What would your answer be? No, it's not continuous, because as you try to go from A to B, your graph has a break in it. Right? That's more mathematical. You have to break and go to the next section. Now, if I put A there and I put B here, is the graph continuous over that specific interval? Yes, not over every interval, but that specific one, yes it is. So some graphs can be continuous in some spots and not in others. Okay. Let's go back here. If a graph is not continuous over an interval, then we just say that it's discontinuous. Basically means that something happened that if you were drawing it, it caused you to lift your pencil. Now we're going to talk about it, but there's three things that can cause you to lift your pencil. Right? One of them is a divide by zero. That's an asymptote. Right? And you might have noticed, I didn't really point it out, but this detect asymptotes. Okay? That's one of the ways you could have to lift it up. This graph right here doesn't have asymptotes. That's a different reason why there's a discontinuity in the graph. Okay? We just call it it's like a break. Right? And there's one more type of discontinuity that's really hard because you can't see it. You have to know that it's there because the graphing calculator can't tell you it's there. Even like my new one, you can't. So we'll talk about what that one's called. All right, so this I just said to you guys. It is possible for graphs to be continuous in some spots and not continuous or discontinuous in others. So let's graph the function 1 over x, and I want you to give me two intervals that are continuous and then two intervals that are discontinuous. Now, I know just by looking at that formula that it's going to have a discontinuity, specifically because it's a fraction with a variable in the bottom. What value are you not allowed to use for x here? 0. Okay? If you're not allowed to use it, and it's in the bottom of a fraction, your graph is going to jump at that point somewhere else. Okay? So let's graph it and see what we have. 1 divided by x. Now, that drew it perfect. Okay? I mean, these should actually continue forever, just getting closer and closer to the axes. It almost looks like it just stops on my calculator, going up and down. It doesn't just stop. It keeps going. But the important thing is the calculator didn't try to connect it. If you turn off that detect asymptotes, it will. All right, so let's take this graph. Let's make a copy of it. We don't need it that big. And can somebody give me an interval where this graph is continuous? You give me two x values. From this x value to this x value. I could draw without lifting my pencil.
Well, do you want infinity?
Let's make our intervals bounded. I mean, technically you could have an unbounded interval because the directions didn't say that, but let's do bounded ones, so actual numbers. Negative 10 to negative 1, sure. And now, you could include negative 10, you could not include it. The bracket in parentheses doesn't really matter. The point is you can trace from negative 10 to negative 1. Can somebody give me another interval that you could trace from here to here without lifting your pencil? Yep.
1 to 10.
1 to 10, sure. There's two intervals that you could trace that are continuous. Now, let's do discontinuous. Can someone give me an interval that if you tried to trace from here to here, you couldn't do it without lifting your pencil? Yeah?
1 to negative 1.
So negative, yep, always start with the low number, comma, high number. Negative 1 to 1. You can't trace because you're passing through 0. Can someone give me one more interval? Yeah. Negative 1 to 2. This time I'm going to make it a closed interval. I cannot trace basically any interval that goes over 0. All right, if you have a number below and above 0, you can't do it in this problem. All right, let's look at the, I'm going to put that step function back up. And I want you to tell me the largest interval you can that is continuous. Now, if I did that in the last problem, the answer would be, well, infinite, right? Because I can trace, if I did it unbounded, I can trace from 1 to infinity without ever lifting my pencil. That's not quite the same here. What's the length? Oh. Let's try again. Sometimes it does that. What's the length of the longest interval you could have there? Yeah, I'm just trying to think it through. Is it 1 unit or is it just less than 1 unit, like 0.99999? So with the step function, it starts like this is 0 and you include it. This is 1 and you don't include it. Because when you're at 1, you've already jumped up to the next step. So technically it's 0 to like 0.9 repeating. So I guess you could say, what is the length of the longest interval? The length, you could say the length approaches 1. And that's getting into the idea of what's called a limit. It's getting closer and closer and closer to 1, as close as you want it to be. Right? It's like 0.9 repeating. But the length approaches the number 1. It gets very, very close to it. All right, so I told you there's 3 different ways that a function can have a discontinuity. One way is if you try to plug in a number that's not in the domain. That usually happens with fractions. Okay? You've got a variable on the bottom, and you can divide by 0. Okay, so that's one way you get a discontinuity. The other way you can get a discontinuity is if there's a break in the graph. It's not that the integer function has asymptotes. Like if you look at it, there's no vertical asymptotes in that function. Right? You couldn't tell me a number that I'll say it a different way. Every number can be plugged in for x here. You can't give me one that can't. I can plug in 2, I can plug in 0, I can plug in -3. I can plug in any number you want right there. So it's not that there's an undefined value. It's just the behavior of the function, the way it rounds numbers, causes you to jump all of a sudden. So any question on the difference between this one and this one? Right. Here, there is a value I'm not allowed to use. The bottom one, no. It's a different reason why there's a discontinuity. And the third one is the trickiest. There's a hole in the graph. Now the problem with the hole is you can't see it. The only way you would know it was there is if somebody showed you the original problem, and then you know what to do from there. Okay, but let's graph that. Now, we know that you can't use what number in this problem? You can't use -2, right? Now, you might say, well, that's kind of like the first one. It's an undefined value. It is, but it looks totally different. You can't see it. So it's kind of like a special case of the first one. It is undefined, but let's look at it. All right, so x squared plus 3x plus 2 divided by x plus 2. Okay, so remember, -2 you can't use. Do you notice anything weird at -2, looking at that graph? It just went straight through it. It doesn't look like if somebody walked in here right now, like if Mr. Babb walked in here and I showed him that, well, he's pretty clever, so he'd probably think I'm up to something. But if a person walked in, they'd probably say, oh, it's just a line. Just a line. It looks like it has a y-intercept of 1 or something like that. Okay? Well, we know if we go to the table, try typing in, let's go to second table setup. Let's make it so I can type in whatever I want. And let's type in -2. But you actually have to type in -2. 2. Error. Doesn't work. Doesn't work. So, what's happening here? Let's look at this. Factor the top. How does x squared plus 3x plus 2 factor? X plus 1, yep. X plus 2. That's the problem. You have x plus 2 as a common factor in the top and the bottom. So what really you're graphing, or what it looks like you're graphing, is this. Y equals x plus 1. It looks like that's exactly what you're graphing. And it basically is, except at the number -2. That's the difference. Okay. The problem in black has an invisible hole at -2. You can't see it. The problem in red actually doesn't have the hole anymore because I canceled them out. So technically, I'm just going to put like an arrow here because those are not the same thing, the one in red and the one in black. They're different because you canceled out something that made a hole. So how would you really show that? If I wanted to show a hole, I'd go like this. I'd draw a line and I'd put a circle around where the hole should be.
But we would know the hole.
The only way you would know there's a hole is if you look at the original problem.
But if we said it was like, you just can't divide by 0, would that still be wrong? Because like, technically...
Well, it depends on the question. If I said to you, is the following graph continuous or discontinuous? Like the whole graph, the whole thing. And you said yes, well, that would be wrong because it's not. And if you said no, and then I said, well, how come? You would want to say because there's a hole in the graph. I would be looking specifically on this one that you know there's a hole here versus like a vertical asymptote. Now, if you change one number here, take this x squared plus 3x plus 2, make it x squared plus 3x plus 3. Now it doesn't factor, right? The top is not going to factor with x plus 2 in the top, and it's totally going to change how it looks. Right? Just by changing that one number from a 2 to a 3. All right? So that's more an example of the first one. It's an undefined value because there's a vertical asymptote. Right? When you have common factors in the top and in the bottom, that's when you get a hole. Okay? Common factor in the top and in the bottom. So really, you can only tell you have a hole if you can factor it. It's the only way to tell. Any questions on those three things? Vertical asymptotes, breaks, holes. Okay, and those are all examples of discontinuities. All right, so every single polynomial is continuous from negative infinity to positive infinity. Remember, polynomials are things that look like this. 3x cubed, 2x squared, plus 4x minus 5. Polynomials never have fractions with variables in the bottom. If you never have a fraction with a variable in the bottom, you're never going to do what? You're never going to divide by 0. So polynomials, you never divide by 0. And polynomials never have square roots in them. You never have like the square root of x. You could have the square root of 3, that's okay. That's just like putting the number 1.7 in front. But you would never have a square root with a variable under it. So you would never be taking the square root of a negative. So the two things you're not allowed to do never happen in polynomials. So polynomials are continuous everywhere. And we call them continuous functions. Okay. Which is even stronger than saying, okay, well, it's continuous from here to here. Well, I'm saying polynomials are continuous from everywhere to everywhere. It doesn't matter where you start and where you stop. Polynomials are continuous functions. You never, ever have to lift your pencil to draw one. Whether it's a parabola or a W shape, there's no breaks, no holes, no undefined values, no asymptotes. Okay. So would the step function be considered a continuous function?
No.
No. No. Could you find a continuous interval in it?
Yes.
Yes, a small step maybe you could, but not the whole thing. So it's not a continuous function. Okay, any questions on the idea of continuity? That's the first thing. Okay, second thing is the intermediate value property. All right, let me give you an example first, and then I'll put up all fancy math stuff. Let's say you had a pot of water and you put water in it, measure the temperature, and the temperature starts out at like 70 degrees. So it's almost like room temperature water. So the water is at 70 degrees and you heat it all the way to boiling. So it goes from 70 to 212. What temperatures is it going to go through in between? 70 and 212. So how many temperatures are there from 70 to 212? Okay. How many? More than that. More than that. Infinite. Right? As the water goes from 70 to 212, it's going to be 70.4 degrees at one point. It'll be 86.2 degrees. It'll be 91.37 degrees at some point. Right? When you boil water, it doesn't skip a temperature. It goes through every single temperature from 0 up through, or whatever you're starting at, to whatever you're ending at. It's a continuous process. Now, what if I count the number of people in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. With that, am I going through every single number from 0 to 12? No, that's called discrete. I didn't hit 1.5. I didn't hit 1.7, 2.4. Right? I didn't go through every single number from 0 to 12. I skipped 1, 2, 3. So the intermediate value property is going to tie in with the idea of continuity. Thinking about going through all the numbers in between a starting point and an ending point, like boiling water. Okay. So, if you have a function that is continuous over a certain interval, we'll just say that that interval is from A to B. So it doesn't necessarily have to be continuous everywhere, but if you can find a small section that is continuous from A to B, then what that means is your function can take on every y value between the y value at A and the y value at B. Let's draw kind of a picture of that. This is point A. The y value, well, I don't know, it'd be plug in A into the function and see what it comes out to, but it would be f of A. This is going to be my B, and what would be the y value up here? I don't know, plug B into the formula and see what you get. So plug B into the formula. So what this is saying is that suppose you have a function that is continuous. Is that function continuous? Yeah, there's no breaks, there's no holes, there's no asymptotes. So that's continuous, so we're good. This is the y value. I'll just kind of put it horizontal. That's the y value at point A. This is the y value at point B. Think about this horizontal line as representing the y values you're going to hit. As I go from, let's take this line. As I go from this, there we go, this y value up to this y value, which y values did I hit in between as I drag the line? All of them. I hit them all, right? Think of that as like the starting temperature of your water and your ending temperature. Even if you heat your water up a little bit and then let it cool off and then heat it more and cool off and heat it, if you're going to get from here to here, eventually, you're going to go through every value in between. You have to. Okay? Any question on that idea? If it's continuous. If it's discontinuous, then no, you may skip. Right? But that's continuous, so you're going to go through every y value at some point. You might even go through the same y value more than once. Looks like I go through that y value 1, 2, 3, 4, 5 times. I'm not guaranteeing how many times you'll go through it, but I will guarantee you go through it at least once. Like that one right there. All right, So let's take a look at an example. So I have a function, f of x equals 3x minus 4. First of all, is that function continuous? Yeah, it's just y equals mx plus b. It's one of the simplest continuous functions you can have. It's a line with a slope of 3 and a y-intercept of -4. Now, I want you to find a value. I want you to find an x value for me so that when I plug that x value in right here, I get a y value of 15. First thing I want to do is see if that's even possible. Do we even, basically what I'm looking for is, if we start at -10, are we below 15? And then if we plug in +10, are we above 15? If we are, then we're good. That means if you started below 15 and you ended above it, you must have passed through the number 15 at some point. It's kind of like if you had water at 0 and it went to 30. Well, there's got to be some point when it hit 15. Okay. So let's see if this is possible. Let's plug in -10. If you plug in -10 for x, what do you get for y? -34. So on this graph, over this interval, because I know a line goes down forever, but I'm just saying on this interval, I'm starting at -34 on the y-axis. And I'm going up to, what's the highest y value that I'll ever hit from -10 to 10? 26. Any question on how we got those two numbers? So, if I'm starting at -34 and I'm ending at 26, am I going to hit 15 somewhere?
Yes.
Yes, because this is a continuous function. So you must have hit 15 somewhere. So now let's just fill in 15 right there and solve for x. So the algebra part of this is very simple. It's just the idea behind it with continuity. Okay, that's what I want you to understand. 15 equals 3x minus 4. Now, before we solve it, we know that the answer has to be between -10 and 10. And based on my y values, I've already confirmed that I'm going to hit 15 somewhere between -10 and 10. Now the question is where? So let's solve it and see. So we get 19 equals 3x, or x equals 19 thirds. Is 19 thirds between -10 and 10? Yeah, it's right in the middle of that interval. We already knew it would be. And that's your answer. Okay. But the idea behind that is the kind of thing I'm going to ask you to write in words and explain on the test. I'm sure everybody can just solve this equation. That's simple. But it's, did you really understand what you just did? Like the idea of continuity. Okay. Let's try one more. So, I want to find a value for x such that when I plug it into that quadratic, I get -3. So first thing I want to do is see if that's even possible. Right, so let's plug in -2 and see what we get. What's -2 squared? 4. 3 times -2, that's -6. 4 minus 6? 4 minus 6 is -2 minus 4. Negative what? -6. Okay, so we know we're starting at -6. Where are we ending? $14. Oops. 14. So, what kind of graph is that, if you were to actually draw it out? It's a parabola. Parabolas are polynomials. Are polynomials continuous? Yes, so that is continuous. Now, important thing to remember about the parabola versus the line. I don't know if this is actually the lowest that it ever goes in this interval. Maybe the graph looks something like this, where it starts at -6, it goes lower, and then it ends up at 14. So what we didn't even really figure out maybe necessarily all the values that it goes through, but we know that from -2 to +3, it'll definitely go through all the y values from -6 to 14. Maybe even a few more. But that doesn't really matter because we're just interested if it goes through which one? -3. And will it? Yes. At some point, it'll definitely go through -3. So now we can solve it. Is there any question on how you would solve that? If you just change this to -3? You might be able to factor it.
You can.
Yeah, if you what?
Yeah, you can.
You can. Let's see what happens. So you get 0 equals x squared plus 3x minus 1.
Oh, okay.
Oh, I thought you you can factor it if you keep the 4 on the side, because then you just get x plus 4 and then x minus.
Well, when you factor, it's got to be equal to 0. If you factor it when it's not equal to 0, then it doesn't help. But yeah, so that doesn't factor. So what would you have to do to finish that? What could you do? You could graph it. You could just see where it crosses the x-axis. Or if you didn't have a graphing calculator. Do what? You could complete the square. Most people don't suggest that one, but absolutely. Or quadratic formula. You'd have to use
-1, right?
What's that?
Wouldn't x be -1?
I'd have to solve. I mean, I can just check it and see. If you plug in -1 squared, you get 1 minus 3 minus 4. 1 minus 3 gives me -2. Minus 4 is -6. No, so it's not that one. Right? It's going to be between -2 and 3, though. But it's probably going to be a decimal. It's probably going to end up being a decimal. All right. Now, what's that?
2.14.
It comes out to 2.14? Okay, thank you. This one's a little different, but very important for the test tomorrow. Example 5 is used basically to prove that your graph crosses the x-axis. You're not asking where. You're just saying, I can guarantee you somehow that this graph will have a 0. Or you could say it will have a root. Or you could say it'll cross the x-axis, whatever way you want to say it, between 0.25 and 0.75. How could I guarantee something is going to cross through the number 0? Someone explain to me what kind of situation we would have to have. Okay? And just as an example, I guaranteed you on this problem that you would go through the number 15. I proved it to you, right? On the next problem, I guaranteed you that you would go through the number -3. We proved it. How could you prove to me that you go through the number 0 here? So think of, you have to use the intermediate value theorem combined with the idea of continuity. And that's basically that we did that on the last 2 problems, example 4 and 3.
Just do the same steps.
Okay, so what would I do first?
Plug in 0.25 into.
Okay, let's plug in 0.25 into function f. I'm going to use my calculator not for the graphing feature, but just because it can do the table faster than I can. So x to the 5th plus 2x. X to the 5th plus 2x minus 1. Okay, so let's plug in 0.25 into my table. Okay, I get basically negative 0.5. Okay, so I did that. What did you want to do next? So plug in 0.75. Let's see what we get. 0.75 gives me 0.737, so we'll just call it 0.74. And these are approximate. Okay, so am I going to pass through 0?
Yes.
Why?
Because it's a polynomial.
What is special about polynomials?
They're continuous.
Okay, let's write that down. So since we have a polynomial which is continuous. Okay, keep going. So I have a continuous function. Yeah. What's significant about it going between negative 0.5 and 0.74? Zeros in between. So since we have a polynomial which is continuous, and f of 0.25 is a negative, and f of 0.75 doesn't matter which positive, it's a positive. Okay, so let me read what we got. Since we have a polynomial which is continuous, and f of 0.25 is a negative, and f of 0.75 is a positive, we must pass through 0. We have to. There's no way to go from a negative number to a positive number without going through 0 and have it be continuous. It's important to mention continuity, because if you didn't mention that, and somebody said to you, well, I want you to count from negative to positives and not go through 0. Sure, I could say count by threes. Negative 2, 1, 4. So I skipped right over 0. But that wasn't continuous. I skipped. Right? If you're continuous, you can't skip over 0.
And how do you do the table thing on the calculator?
To do the table thing, you go to second table setup. Make sure it looks just like that. And then you go to second table, and you can type in anything you want once you do that, as long as it actually comes up. Yep. Okay, so very important idea for tomorrow, to understand how the idea of continuity and the intermediate value theorem proved that there's a 0. 0 is an intermediate value between negatives and positives. It's right in the middle. That's what intermediate is. Okay, so last thing we'll look at, probably the easiest thing, is the end behavior of a function. So end behavior is predicting what a function looks like on the extreme ends of it. Like really, really far to the right, or really, really far to the left. We're not really focused on all the little twists and turns in the middle. We're looking at what happens, like if you zoom way out, what does your graph look like? So let's take a look at y equals x cubed. Okay. Simplest cubic you can draw. Y equals x cubed. We go zoom 6. Okay. So what we're interested here is describing the end behavior. What happens on the left side of the function? What happens on the right side of the function? This describes the behavior. On the left side of y equals x cubed, your graph is heading down. On the right side of y equals x cubed, your graph is heading up. Now, that's one way to write it, just using little arrows. As you head to the left, what's happening to your x value? As you head further and further and further left. And getting closer to what? It's getting closer and closer to negative infinity. Does it ever reach negative infinity? No, you can keep going. You'll never reach it. So, this is another way to explain what's happening right here. I'm going to do the bottom one first, just because I already asked you guys that one. As you head further and further left, as x approaches negative infinity, the question is, what is happening to your y value? What's the y value approaching on this graph? as you head further and further left? Right, it's heading down, which is like a picture, but down means this. So this, remember, f of x is just another name for y. So this says the limit of the y value as x heads to the left. Or if you want to read it formally, as x approaches negative infinity. So as you head to the left, your y value is heading down. What about the limit of the y value as x approaches positive infinity? It's going up. That's what we said right here. Up means positive infinity. Okay? So polynomials always involve infinity and negative infinity. Always. That's always what the y value approaches. You have to figure out if it's positive or negative. And I'm going to show you a little chart for how to do that without even making a picture on the calculator.
So we can do it that way.
Yeah, you can do it either way. I will tell you, you'll see both notations. In calculus, you will see the one on the right. They'd kind of laugh at you if you did this on the left. It makes sense, but it's not. This is not really calculus, where the stuff on the right is more calculus type stuff. So there's 4 types of n behaviors. Both ends go up. Both ends go down. One down, one up, one up, one down. We just did this one. And you can write each one of these in limit notation. That's what's on the right. This is called limit notation. This thing with arrows on the left, we'll call it arrow notation. I don't know. It doesn't really have a name. But those are the only 4 things that can happen with polynomials. And which one of these cases you have depends on 2 things. It only depends on 2 things in the whole polynomial. Doesn't matter how long you make it. There's only 2 things I have to look at, and I'll instantly know which one of these 4 it is. Does anybody have any questions on how you write things in limit notation? So as x approaches infinity means as you go to the right, what's happening? As x approaches negative infinity means what's happening on the left. So this is this. And that, did I circle it? Yep, did it backwards. Hold, sorry. That is that. What's happening as you negative infinity means as you head left. That's my left. This is on the right. As x approaches infinity means head to the right. So let's see if we can just identify the end behavior in this one. And then I'm going to show you a little chart, a little pattern. Show you y equals x to the 4th. So now instead of x cubed, we're just going to change it to a 4th. Does anyone have a guess before we graph it?
They're both going to be up.
Yep, they're both going to be up. It's going to look kind of like a parabola, but a little flatter on the bottom. So this one is up, up. How would I write, let's just do this one first. How would I write this in limit notation? The limit of what comes next. Yep.
Say like negative or as x like reaches.
Approaches, yep.
Negative infinity.
So she's doing this one. The limit as what approaches negative, as limit of the what value as x approaches negative infinity. Yes, which basically means y. So the limit of f of x, or the y value, as x approaches negative infinity, what's happening?
The y goes to.
Yep. And the limit of f of x as x approaches positive infinity, as x heads to the right, what's happening? It still approaches infinity. I'm not going to write it both ways each time. Does anyone have a guess what this one's going to look like? Yeah, think of the negative in front when we studied transformations. That's a flip. It's a reflection over the x-axis. This one is down, down. What do you think in these two equations makes them either both go up or both go down? Why don't you have an up-down like the one we just did? Yeah?
It's a grab.
Well, this can turn up to 4 times, so it could look like a W shape if I added more stuff to it. But how is this one different than y equals x cubed? Because y equals x cubed had an up-down. Y equals x to the 4th didn't. What's the difference? This had an up-down. This didn't. What's the difference?
The degree is even and odd.
It all depends if the highest exponent is an even or an odd. Okay. So, we're going to kind of summarize whether it's even or odd. And the other, I said you have to look at 2 things. The other thing you have to look at is the number in front of the highest term. So if you had this, 8x cubed minus 4x squared plus 6x minus 5. You know what? If I want to know what this is going to look like, I don't care about any of that. None of that makes any difference at all. What that stuff does that I just crossed out, it's going to cause little twists and turns in the middle. But this number being odd and this number being positive is going to control the end behavior. So, there's basically 4 cases. Whenever you have an even exponent, the behavior is the same on each end. Up, up, or down, down. If it's an even exponent and the number in front is a positive, like I have right here, 8. Greater than 0, up, up. If the number in front is less than 0, like if I made this a negative 8, now the behavior would be down, down. So for me, even and odd, that one's easy to remember because I just think of a parabola, y equals x squared, up, up. Odd is a little harder because you got to remember it's 1 up, 1 down, always. If the number in front is greater than 0, it's down, up. That's like this. Down on the left, up on the right. If it's an odd and the number in front is less than 0, it's up, down. That would look like this. Up on the left, down on the right. And it may even take more twists and turns than that. Maybe it does something like this. But the point is, overall, it's up on the left, down on the right. Yep?
When you're writing like the limit approaching infinity and approaching negative infinity, you don't have to like notate it like the limit from the left and from the right, right? This is not like a definite value.
So if they ask you to describe the end behavior, then yes, you have to write 2 limits.
Yeah, but you have to like notate it like from the left and from the right. Right?
The way you notate it left and right is x approaches infinity is the right, x approaches negative infinity is the left.
Okay.
Yep. Okay, so that's a chart that'll quickly tell you end behavior. Just looking at the highest degree term and the number in front. So, the leading term in the polynomial, it controls the whole thing. So you really don't need to write that down. We just said that. If you want, you can. So the leading term is the one with the highest exponent. It controls the whole polynomial. Think about like cubing something versus squaring it. For small numbers, it might not make a big difference, but when you get into big numbers, think about like 50 squared versus 50 cubed. 50 cubed is way bigger. 50 squared, it's like not even that big compared to 50 cubed. Right? So highest degree term controls everything. And that one all by itself predicts the end behavior. So, the last thing we can do knowing this is they may give you a really complicated polynomial and ask you to write what's called an EBM, end behavior model. So, in order to write an end behavior model of some really long polynomial, the only thing that matters is that, the leading term. What I just put a box around, that would be the end behavior model for f of x. That's all you write down for the EBM. You basically erase everything after the highest degree term, assuming it's in descending order, which I usually do. Highest one first, and then it goes down from there. So g of x is called the EBM, end behavior model. Any questions on that? So it's very easy to write an EBM. There's no math involved. You just basically take the highest term and erase everything else. Okay, so let's start with that. Can somebody tell me what would be my end behavior model? It would be 2x cubed. So let's graph both of them, because the end behavior model should look kind of like the other one. The EBM won't have all the detail, won't have all the twists and turns, but the big picture will look exactly the same. So let's graph it. They first tell us to graph it in this window. That's your x min max and then y min max. Let's see if they look the same. 2x cubed minus 7x squared minus 8x plus 16. Okay, and put in the EBM, 2x cubed. Okay, window is negative 8 to 8 and negative 100 to 100. Now, is negative 8 to 8 a really zoomed out view? No, that's a really zoomed in view. So when we look at this, they're probably not going to really look that similar because we're zoomed so far in. Do those look the same? No, they're not really the same. Now, let's zoom out. Okay, let's zoom way out and see how they look now. So let's go negative 40 to 40, and let's go negative 10,000 to 10,000. I'm going to ask the same question. That's the really detailed one right there. And now here comes the EBM. Do those look the same?
Yeah.
Pretty much. They look pretty much the same. So when you zoom out enough, the end behavior model will look just like the real complicated one. It's a simpler version of it, without all the detail in the middle. Okay? So all we had to do was graph. That was it. How about, what's the end behavior model in that one? Negative 0.5x to the fourth. That's it. That's the EBM. Any questions on how we found it? I'm not going to graph that one. The original could look like a W shape. And what would the end behavior be of this one? Up, up, down, down, up, down, down, down. So it could look something like this, where this one is going to look something like this. But zoom out enough, and you won't even see those little ups and downs. We did that, we did that. We're not doing that, so that's it. Okay, so the homework tonight is on 161, and it's 1 through 6, 9 to 12, 15, 16, 21 to 25, 29 to 31, and 33. Okay, so tomorrow we have our test. Progress report's closed tomorrow. I'll be after school today if you need any extra help.